Dear friends, today I would like to talk about some refrigeration systems, and what you will see here, this is a configuration of some electrical wiring. Why I want to show you this is very important because sometime when you'll have electrical faults, the problem can be triggered from other devices that you can even imagine. If the electrical system it is not well designed, then there will be distribution boards which affect other distribution boards, and it will lead you on a wrong pathway when you'll do your investigation. As you'll see here, if you can follow my mouse, I'm not sure if you'll see it, I'll show my finger. So if you'll see here, this is the MCC, the main place where the all distribution boards get power. Then you have the distribution boards. As an example, down here you have two distribution boards which supplies power to variable speed drivers that supplies power to the motors. It could be compressors. Now these variable speed drivers get their control sequence from a control panel that takes its power supply from another distribution board, and this distribution board gets power from another distribution board which supplies power to another distribution board. So you see you have like a tree of power supply, and when you do your investigation you can have a local investigation to see why your motor tripped, but in the same time you might have like this distribution board tripped, and then you will have to go step by step to investigate until you reach the core of the problem. I will talk more in detail in another video. This video is just for refrigeration, and I just supply you a little bit of information. What do you have to talk here on this video? It is this, hope you'll see better, but you'll see better because I'm going to put the movies. You have the thermostat, you have the overload, you have the oil, then you have the low pressure switch, high pressure switch, and there can be any other alarms. This is a bad system from my perspective because all alarms are in series with the thermostat, and this sends the input to control an alarm. So you always have a general alarm. If you have an issue with the system, it won't tell you what's wrong with it. If the client wants to spend more money, he can use either building management control or a programmable logic controls. I have other videos. If you look, they can be individually wired into the programmable logic control inputs, and then you can have each fault individually, and that's a little bit convenient for the customer and for the technician, because any fault can be identified much faster, and then the customer can save a lot of money. Imagine you want to meet the refrigeration system. Let's run to the entire system. On the right hand side we have the compressor. As you will see, inside the compressor you have a moving part. That's the crankshaft and the piston. What that piston do? It takes this superheated refrigerant from the lower side, from compressor crankcase, and it pushing it towards the condenser. Then the refrigerant goes further through the thermostatic expansion valve into the evaporator. Then it's coming back into the compressor crankcase. Now let's go a little bit deeper. The refrigerant goes from the compressor into the gas line. The gas line, it is between the compressor and the condenser. In that area, the refrigerant, it is extremely hot and under high pressure. In between the condenser and the compressor, we have the oil separator. The oil separator allows the oil which is taken by the refrigerant to go back into the compressor's crankcase. Then the refrigerant goes to condenser where it is cooled, and then it goes out of the condenser to the side glass, to the filter dryer, to the receiver, and it reaches the thermostatic expansion valve. The thermostatic expansion valve restricts the refrigerant flow and divides two areas, the higher pressure side to the lower pressure side. The evaporator is under low pressure, and because of that, the injected refrigerant boils. When the refrigerant boils, it absorbs heat and then superheated continue its journey. So let's start again. When the compressor starts, the refrigerant starts moving to the system. So the heat advancing from the compressor towards the condenser. When the condenser reaches the critical heat, the condenser fan motor starts. And the refrigerant, it is subcooled. What does it mean subcooling? The refrigerant have to leave the condenser with 8 degrees less than the necessary temperature to liquefy. Then the refrigerant goes into the receiver and it reaches to the text valve, the thermostatic expansion valve. The thermostatic expansion valve restricts the refrigerant and control the superheat. What does it mean superheat? As you will see, the thermostatic expansion valve have a little bulb underneath the pipe at the evaporator exit. In that point it controls liquid not to go out from the evaporator or excessive liquid quantity. And that's because we don't want a liquid to come back into the compressor. Otherwise we will destroy the compressor. So the refrigerant passes by the evaporator where it's boiling and absorbing heat, and then superheated goes into the suction line towards the liquid separator. Because sometimes we cannot control perfectly the superheat, we use a liquid separator. The liquid separator helps us to split the liquid to the vapors. We don't want liquid droplets to go into the compressor crankcase, otherwise we will destroy it. As you will see in this picture, liquid sits to the bottom while the vapors to the top goes back into the compressor crankcase to be recirculated. This is a full refrigeration cycle, and as long as the charge is okay and the system is not abused, I will explain to you about the humidity and the outdoor temperature, the system will work. I just want you to bear in mind that compressor it is cooled with the refrigerant which return from the evaporator. So you do not have to apply too much or not enough superheat. Otherwise, you will overheat the compressor and the compressor will be damaged. You will see now pulsing the low pressure switch, the high pressure switch and the text valve. So while the refrigerant moves through the system, the low pressure switch, the high pressure switch and the text valve are constantly monitoring the refrigerant. The high pressure protects us against the high pressure. If the condenser fan will be broken and the condenser will get very hot, the pressure will increase into the system. The high pressure will cut the electricity to the compressor. The low pressure switch protects us. If the refrigerant leaks from the system, we don't have refrigerant, the pressure gets very low, and then it will cut the electrical system to the compressor. Thermostatic expansion valve controls the superheat. If we have as an example a refrigerant leak, or if the system it is under charge, the low pressure switch will cut the electrical system to the compressor. But many systems in a commercial area using this automatic reset low pressure switches. So anytime the low pressure switch will stop the compressor, when the compressor stops, the refrigerant balance into the system and it will restart it again. That is called short cycling. I usually put a timer which will latch if the low pressure switch cut more than 3 times the compressor in a specific period of time. Compressor gets very hot if you starve the system of refrigerant. Look, the evaporator, it's only half iced up, and the suction line is warm, so it's not enough refrigerant coming into the compressor, and the compressor gets red hot. Soon the compressor will die. If the filter dryer gets blocked, if you look to the filter dryer in between the condenser and the evaporator, you'll observe that the refrigerant, the pipe, gets cooler immediately after the filter. You will starve the thermostatic expansion valve and you apply too much superheat. You get the same phenomena. Half of the evaporator will be iced up, but then the HP will trigger a fault, will cut the compressor because you will collect all the refrigerant inside the condenser. If you overcharge the system, that's worse. If you overcharge the system too much, the liquid will come back into the compressor crankcase. See? If you see to the lower side, the liquid separator is full, and then you will brush the oil from the compressor crankcase and you will destroy the compressor. If you have a dirty evaporator, or if the evaporator runs long hours in a humid environment and it's on negative temperature, the evaporator ice up and the fan motor will get hot because you won't have enough air to suck. The low pressure switch might cut the system, but can you imagine, you cannot apply superheat anymore, and then your compressor will ice up. To avoid this phenomena, we apply defrost, but many systems are using defrost based on time. It will be a time defrost which will enable a heater element or will invert the refrigerant cycle, so we push hot gas into the evaporator to melt the ice. This is a choice, but not the best choice, because the time will disconsider the environment. We might have more or less humidity, so the contamination can happen fast or less fast. Anyway, after the defrost, when the ice melt, we have to allow the water to go into the drip tray and to be eliminated. Then the cooling cycle will start again. This is the refrigeration cycle. The compressor pushes the refrigerant towards the condenser, and you'll see the red cylinder in between the compressor and the condenser. This is the oil separator. While the refrigerant can transport oil in that cylinder, the oil will drop to the bottom, and when that will fill up, it will be a valve which will open and you will allow the oil to return into the suction line or into the compressor crankcase. Best is straight in the compressor crankcase, but I've seen the oil goes into this suction line and the refrigerant will take it back into the compressor crankcase. And then the refrigerant is cooled, continue its journey to the thermostatic expansion valve, where it is restricted and injected into the evaporator. Into the evaporator will absorb the heat, and the supercooled refrigerant will return through the liquid separator into the compressor crankcase. If you look to the gauges on the compressor, on the high side the pressure is bigger than onto the low side. I didn't put numbers because it's up to you to see what refrigerant are you going to use. What you see here with yellow, I marked the area where the pressure it is high, but I want you to pay attention to the right hand side in between the compressor and the condenser. There's a very hot pipe. There's a very hot pipe. The superheated refrigerant under high pressure. You will burn your hands. Once the refrigerant passes by the condenser, it won't be hot anymore because the condenser will cool down the refrigerant, will liquefy the refrigerant under constant pressure. Dropping in temperature will allow the refrigerant to be liquefied, and then the refrigerant will go into the liquid line towards the receiver cylinder, and then will be injected through the thermostatic expansion valve into the evaporator. Because the evaporator have a low pressure, the refrigerant will boil inside, and by boiling will absorb heat. Towards the end of the evaporator, when it goes out, the refrigerant should be superheated. How can you control this superheat? If you look at the thermostatic expansion valve, it's got to the exit of the evaporator connected a bulb. That one can be put at 3 o'clock, at 6 o'clock, at 12 o'clock. You have to control the amount of liquid that goes out on that point, because sometimes we have a very long piping and we have to make sure that we not starve the compressor. Near the valve of the suction line, near the LP, when we check the superheat, ideal will be to have 10 degrees over the boiling point of the refrigerant. But as I said before, I can't give you numbers because I don't know what type of refrigerant are you going to use. For that operation, you have to use refrigerant charts. Make sure sometime you have to check your refrigerant if you're not familiar with the job, because many technicians been before you, and as company starves of money, some engineers or some companies or some customers will only tell you, don't do the vacuum, don't reclaim the refrigerant, just top up the refrigerant. And we all know that by topping up the refrigerant, we might have a different type of refrigerant in the end, because when refrigerant leaks, it's losing its properties. Come back again to this picture. What can I say? I come back to this yellow mark. That's the highest pressure side, and the higher pressure side is in between the compressor discharge till the thermostatic expansion valve. When you go over the thermostatic expansion valve onto the evaporator until the compressor suction, there is the lower side. So what the refrigerant do? The refrigerant absorbs heat through the evaporator and it dumps that heat to the condenser. You have to make sure both fans are running. If you have an evaporator fan which is not running, you will experience an icing up phenomena. If the condenser fan is not running, the pressure will go very high, so the high pressure switch will cut the electrical power to the compressor. It's very important as well, as I said before, to pay attention to the pipes in between the compressor and the condenser. They're extremely hot and they will burn your hands. The superheated refrigerant might have probably over 100 degrees Celsius, because to superheat a refrigerant at plus 12, 15 or 20 bars, you really need a lot of temperature, and that gas will only be cooled and liquefied when it's passing by the condenser. Once that gas passes by the condenser, the temperature will be dropped, and then you have to see what temperature you have to apply at a specific pressure to refrigerant to be superheated. If you overcharge the system, I'll repeat what I just said, you will have the very bad surprise. Your system become inefficient, but a lot of liquid will return into the crankcase. You will sweep the oil from the crankcase and will push it into the condenser. The oil separator will be overwhelmed, and the worst scenario is the liquid goes into this piston cylinder, and as everybody knows that liquids are not compressible, imagine when the piston will try to push the liquid with that speed towards the condenser. What will happen? You will destroy compressors valves, you can damage the piston, and As I said, it's not good to put too much refrigerant to overcharge the system, hoping that the system will run better, because you won't be efficient. You need to have a ratio in between suction and discharge, so the refrigerant boils, and if the charge is properly done, it will boil all across the evaporator. If your system it is under charge, let's repeat this one more to understand it better. The pressure won't be enough and the thermostatic expansion valve will be starved, and the evaporator will be iced up only on its beginning. Towards the end, the evaporator will be warm and the suction line will be warm. That means the refrigerant will be superheated before it will leave the evaporator, and the compressor will be starved. Sometimes can go on negative pressure, and that will make the compressor to suck the oil from the crankcase and to push the oil to the installation. Compressor will get red hot, and with a high temperature the compressor will prematurely die. So make sure you're not undercharged. This is again the same situation. The system it is not undercharged this time. You start losing refrigerant. In this case, the low pressure switch will start to short cycle the compressor. If you have an electronic device that counts how many times the LP will cut the compressor in 1 hour or 10 minutes, you're safe, because after a while it will cut it up and it will not restart it. Icing up phenomena will destroy the evaporator fan motor, because you will get the evaporator fan motor cool itself with the air which passes by. That can happen because your evaporator is dirty, or you didn't apply the correct defrost, or the environment where that heat exchanger is running, it is very humid, and you know, if you have a heat exchanger that runs on negative temperature, the ice will build very fast on that evaporator. So you have to be very careful to have a clean evaporator and to apply the correct defrost, otherwise you will have this bad phenomena and you will lose system's efficiency. The defrost based on a timer is not a precise defrost, yet it is a defrost. The time wouldn't know the value of humidity percentage into the room. So after the defrost, you have to allow the water to go on a drip tray and to be eliminated, and then you will restart the refrigeration cycle. What can I say? When the defrost is done, you will start to cool the evaporator again, and as long as you will not bring too much liquid in the compressor crankcase, as long as you'll have the evaporator clean, as long as you'll have the condenser clean, as long as you check the fan motors so they run properly. You also have to check the oil separator valve or actuator if allows the oil to come back into the compressor crankcase. You have to check the low pressure and the high pressure switch to see if they work correctly. Sometimes you have to calibrate the manometers to see if they shows you the right pressure. If you look here onto the discharge, you have a high pressure, onto the return you have a low pressure. That's the ratio which allows you to create the refrigeration process. You really have to be careful with this ratio. You have to check what refrigerant are you using, and you have to apply the correct pressure difference in between discharge and the suction. Many refrigeration engineers are enjoying that they creating cold, but the system with many occasions doesn't perform more than 60 to 70%. If you want to find more about heat exchangers, ice contamination. If you want to find out how to build your own heating system at home, or how the pumps are working, about the programmable logic control, how can you integrate air handling units, boilers, chillers, or if you want to find out about the basic air conditioning system, or how to build a relative humidity control in air handling unit, or maybe you want to know about contactors, how they work and how they enable big loads getting very small signals from little switches or programmable logic control, just subscribe. As you'll see, this is a basic contactor, and with the 24 volts power supply from a switch, I can enable a 3-phase main power to a compressor, to a motor, or to anything. So with the contactor with small signal, I can control heavy electrical loads. If you don't have a switch, you can use a programmable logic control. See, I just turn on the main power supply to the motor, but the motor is not running. If you look to the programmable logic control on the left hand side, you have a little switch on the top in the left hand side, and is not enabled. The PLC holds off the main contactor, so the motor is not running. And I want you to look to the PLC. Now the PLC enabled the contactor, and the electromagnetic, all of the contactor, close the 3-phase circuit, and then the motor spinning. If you look to the bottom of the contactor, you will see the programmable logic control have the ability to send the signal to that contactor, and the contactor closes the circuit. You will send the signal back, which will tell him that the contactor, it is healthy. Thank you very much for watching my video. So I see you next time. Bye.